Hello, strangers. Welcome back. Let's talk about a concept that is, well, I don't know, challenging, but seems a little bit strange in some cases. And it's this concept of work in a physics context. All right, and we're going to talk about whether or not work is done, again, in the context of what we mean by work in physics. Well, work is done in 4 different cases. First, here I am. Oh, here it is. Here's that bowling ball. I'm holding the bowling ball stationary above the ground. Am I doing work? Or is there work being done on the ball? You can pause if you want, think, take a choice, make a choice. Go, pause. Welcome back. So, did you pause? Better have. Well, no, there's no work being done here. You know why? Well, because nothing moved. Okay, forget about a box. I'm going to lift this bowling ball vertically. That's a good one. Yep, there it goes vertically. Is there work being done? Pause, think, answer. See, I don't think you paused. That's why I'm just waiting. Come on, think. Sure, okay, yes. So, yes, there is work being done here. Why? Well, the ball, the box, moved. Okay, here's the ball. Forget this box. Here's the ball. Can you hear it sliding? I'm pushing it across the table. Work being done? What do you think? Yes, there is work being done. Why? Well, again, the ball moved. There's something else that we haven't talked about yet. There's something else that's happening. It's not just motion is happening. We'll also say here, the ball moved because I pushed it. Same thing here. The ball moved because I pushed it. So a couple things we need in order for us to say that work has been done. We need a force, and we need something to move because of that. All right, so case 4, I'm going to take this ball. Okay, I'm holding it. I'm walking across. Here I am. See you later. Can you hear me walking? I'm all the way over here. Coming back at you. I'm right next to you. There I go. Yeah, so I'm carrying this ball around the room. Now, I should say at a constant velocity. I'm walking at a nice constant velocity. Is there work being done? Well, we're going to come back to that. Remind me, we're going to come back to that one. Okay, so by definition, work is done if, when, a force applied to an object results in that object's motion. No, that object's motion. Need those 2 things. And shocker of shockers, the more force you apply, the more work you do. The farther you move something, the more work you do. Fair enough? So, F D right? Measured in, I should put that in square brackets, shouldn't I? Well, so sorry, I can do it like this. Force measured in newtons, distance measured in meters. So yeah, work's measured in wait a minute, Newton meters. Newton meters. Haven't we heard of the Newton meter before? The wonderful Newton meter? We have. And a Newton meter, by definition, is a joule. So work, most commonly expressed in joules. Newton meters is fine. Kilogram meters per second squared times meters is fine. Kilogram meters squared, wait, you know what I'm saying. Joules. There's a little hint for you about what's coming. All right, so here's the most basic equation you can use to calculate work. Here's a force, a 40 Newton force, sliding an object 6 meters. How much work is done? Why not? Okay, well, it looks like 40 newtons times 6 meters. Work is about 240 joules. Correct. Worth pointing out how much work is done by the force. Sure. How much work is done, version 2, on the object? Same questions? By the force on the object. It's okay? It's okay. Oh, huh. Now, you'll notice, I didn't draw the rest of the free body diagram. No mg, no normal. Fine. We're just talking about this force F that's doing this work. Same thing here. I'm just going to say, well, here's a force F here that's, that is responsible for moving this object, sort of, right? Well, I don't know. Does that 40 Newton force move the object? Remember, here's a vector that I'll call D. Well, it might not surprise you to hear that it's not all of force F that's responsible for moving that object in that direction. It's only this part of the force. Call that F parallel. Call this perpendicular. There's an angle. So we really have to adjust our equation. The real important part is that. It's not going to be weird. Get rid of that little dot. F parallel D. We want only the component of the force that's parallel to the motion. And I could even go a step further. You don't ever have to bother with that. The parallel component of vector F the component of vector F that's parallel to vector D. D being displacement. Yeah, but really displacement, right? Object's displacement. So why isn't it F delta X? Sure, fine, write it F delta X. Just it's more common to see it as FD. Okay, notice, right? That's why we said, but if when a force applied results in that object's motion, and like we said here, it's really only F parallel that is the results in the object's motion. All right, so here we say F. What am I doing? Work is F parallel D. Or work is F cosine theta D. Or work is, let's see, 40 newtons times cosine of 30 times 6 meters? Please to answer. Okay, what do we call this? A connection. A connection. You can fast forward if you'd like to the next slide if you don't want to listen to the connection. Here's what you're doing. What we're really doing, and I wrote it like this a minute ago. Work is what's called a dot product. A dot product of two vectors. We said that work is F dot D. Notice that work, just like energy, is not a vector. Work is a scalar. But what this means, by definition, in math class, I really think you've done dot product stuff. And when you do that, you look at the component of one vector that's in the same direction as another vector. And the very definition of a dot product is magnitude of one vector times magnitude of another, times magnitude of another vector times the cosine of the angle between them. That's the definition of how you do a vector operation called a dot product. Well, why is it that? Well, because, well, look, here's F cosine theta times D. Right? It's finding us the component of one vector that's parallel to another. Okay? All right, connection time is over. I think you've maybe done that in math class. Okay, let's look at a couple of different situations here and talk about something awesome, interesting, unique, not unique, but yeah. A crane lifts this wrecking ball 25 meters at a constant velocity. How much work does the crane's cable do? Sure. How much work is done on the wrecking ball? How much work is done by the tension force? Any of those things are fine. Well, work is FD, or T, tension force, D. Well, you know, if we really look at it, at a constant velocity, mg times d. Well, work is really mg. The d is really delta h. Well, that sure looks familiar. Right? Work and energy measured in the same units. In this case, equivalent, well, work is a change in energy. Solve. Yeah? Okay. Pull up a frictionless cell at a constant velocity. How much work is done? Well, you certainly start if you know both of those. If you know both of those things, just do that. Right? Again, anytime you just know F and D, not F and D. If you know F and D, just multiply them together. Right? And we'll say, I don't know, here's a D goes that far. Well, how much of a force do we have to apply to move this thing up a frictionless incline at a constant velocity? Well, that depends. Sure. Right? Angle. Well, that force is really mg parallel times d. Right? Right? Check this out. Same thing, right? mg sine theta times d, same as mg d times sine theta. What's that? Guess what that is? What? Yep. Oops. Same thing again. Solve, please. Let's look at this one. A mechanic pushes a car of mass m from rest to a speed v, neglecting any mechanical energy losses. I don't know if I should say this. Neglecting any friction. Maybe mechanical energy losses is okay. How much work is done? Well, force. A, right? Applied force. Sure, mg. Normal, why not? Well, work equals FD. Again, if they tell you F and they tell you D, and you want to know how much work is done, just multiply them together. But they haven't told us either of those things here, but we could say that based on a net force statement, this is really, well, A times D. And A is MA, acceleration A, applied force A, right? Times D. Or I could write that as MA delta X, right? Wait a minute. A delta X. M times A delta X. A delta X. Oh yeah, hang on. There's this equation that says V squared is V naught. Well, forget about V and V naught. Let's call it V final and V initial. A delta X. Agreed? So work is M, right? Here's our M, times A delta X. So work, take out this 2 like this, right? Whoa, wait a minute. 1/2 mv final squared minus 1/2 mv initial squared. Whoa! Isn't that just change in kinetic energy? Now you can't solve this one, I haven't given you any numbers. But if I did, here's what you do, because this is what we're saying. And so we've sort of seen a pattern here, I think, I hope. Work caused something to happen. Work caused the same thing to happen. Work caused arguably the same thing to happen. By definition, work is done when force applied to an object results in that object's motion, sure. But conclusion, work always causes, and furthermore is equivalent to change in total energy. Or we can say that work equals change in total energy. Right? Work's measured in the same units that energy's measured in. There's one reason why. Let's go back to page 1. carrying a bowling ball around at a constant speed in a straight line is work done. You answer and tell me why. Okay? Yeah. So, what we're saying now is that work is equal to delta E total. Work changes energy. So in a case like this, let's talk about what energy changes take place. Well, we've done this one, right? Lifting an object. This could happen in really in two ways. I should have done an A and a B for this. A, at constant speed. Well, if you lift an object at constant speed, what energy changes, or what's work equivalent to? Just a delta GPE. Right? If you lift an object, height changes, and therefore GPE changes, and therefore we could literally say that the amount of work done is equivalent to delta GPE. Right? Lifting an object at a non-constant speed. Well, there's a GPE and there could potentially be a KE. All right? Here's me. Listen, right? I got the bowling ball. I'm holding it. I push it up and I stop. Now, while I did that, the object did change speed, right? It stopped, push it up, stopped again at the top. Right? So the speed did change, but if we talk about the initial and final speed, they're both zero. So in that case, it would really just be delta GPE. But there could be a case where, we're not talking about the initial part being where I'm holding it stationary, the final part being where I'm holding it stationary again. We could talk about, I pressed it from here to here, but how much work was done going that far? Well, when I got to this height, it still was moving, it was still speeding up, right? So there we could include a delta KE element. All right. Yeah, okay. Let me go over here, and I push something across the flat ground. Well, if that's frictionless, what has to happen is the object is going to speed up. If I apply a constant force to an object where there's no friction, the object's going to speed up. But flat ground means there's no delta H, so here it's just delta KE. Now, if it's not frictionless and it's frictionful, well, a couple of things could happen. One, maybe, depending on how hard I push, we could change speeds. Put a question mark there. But for sure, if there's friction, we have to talk about that surfaces get warmer. We've been referring to this as thermal energy. All right, now we're going to call it internal energy. Energy of the particles of an object, or the particles of an object. So literally, things get warmer. That's because the particles in them are moving around faster. We can capture that as what we call delta Q. We're not going to capture the sound thing. Okay? So for sure, if there's friction, there's a change in internal energy. There might also, like I said, if I push with more force, if we have this case, friction force that big, but I push that hard, well, that's enough force to speed it up also, to make it accelerate, right? And I'll increase the system's internal energy. Okay, and finally, sliding an object up a rough incline, right? Well, there, for sure, we change GPE. For sure, we change Q. friction. And maybe we push hard enough to speed it up also. So there's a certain minimum amount of work you'd have to do to raise it up a certain height, you know, and overcome friction. If you did more work, you could also speed it up. If you pushed hard enough over that distance, you could also speed it up. Okay? Yeah. Notice, we've been talking about forces done by, work done by like tension forces and applied forces and stuff like that. Really, what we've referred to as non-conservative forces. So what we usually say is that WNC, work done by non-conservative forces, is delta E total. All right, where that might end up looking like this. Well, that could be like delta GPE, whoops. And delta KE, and delta Q. And this could be written as, well, let's see, GPE final minus, oops, GPE initial. And this could be, whoops, right, KE final minus KE initial. And then this, we never do Q initial and Q final. We don't, we just, I mean, could you do it? Sure. Will we? No. Right, equals WNC. But remember, you know, this looks like, holy crap, I have to do all, you don't necessarily always have to do all this. The very, very simplest case is, like we kept saying, if you know F and D, multiply them together. Blah. That's it. If they give you other things, figure out what kind of energy changes. Is this a case where something's changing height? Well, I need a delta GPE term. Is this a case where something's changing speed? Okay, I need a delta KE term. Are they talking about friction? I probably need a delta Q term. Oh, and so furthermore, what we could do is say this. We know that WNC comes from a non-conservative force acting through some distance. And that will give us a change in total energy. So we can not only say how much work is done by a non-conservative force, we can say what is the average value of that force. Okay? Okay. We'll get to that one when you come in next. And you have a few things to calculate. You have one thing to answer on the very first page. All right, the big important stuff. One, work. Changes energy. They're measured in the same units. Only if parallel does work. What else? I'll just say it. And what I mean by that is I think I've said it before, but I'm not sure. Work's a scalar. it can be negative, right? It's not accurate to say, well, the work was done in the negative direction. That's not a good thing to say. That implies that work has a direction. But I want you, let's talk about this also. Can you come up with an example for when work would be negative and why and how? Lots of answers to this. Lots of different ways to slice and dice here. All right, folks. All right. See you soon.